So hello everybody to our first learning lecture in this semester. And I'm very happy to host Eran Malach that will talk about learning the unlearnable. So Eran, now the stage is yours.
Hi. Okay, thanks. So yeah, this is Learning the Unlearnable. I'm Eran Malach, and this is based on the work with Shai mainly on two papers. One is with Shai Shalev-Schwartz, and the other is with Amit Danieli. I'll give the references at the end. And yeah, I'm a PhD student at the Hebrew University, working with Shai. Yeah, so before we talk about learning the unlearnable, I'll start with what should seem kind of obvious, the question of what is learning. So yeah, I guess this is the learning club, so everyone knows what is learning, but I'll give somewhat more formal definition. So just a couple of definitions to start with. I guess everyone should be familiar with these type of notations. So we have an input space, which is basically the space of the examples, the input examples that we want to learn. Most of the results would be valid for general input spaces, but sometimes I'll just assume that the input is a set of n bits to normalize normalized to the unit sphere. So just 0, 1, 0, 1, but we normalize it so that the input would be nice. The label space we denote by Y. I will focus on binary classification tasks. So yeah, this is a supervised learning of binary classification tasks. So this is the main focus. We have the loss function, which typically gets a number and a label and outputs the loss on the prediction with respect to the label. And I will mainly focus on the hinge loss, which is a popular choice for classification problems. And for two functions, one is from example to label. This is the function f, and a hypothesis, which is a function from example to some number. And some distribution over examples. I will define the loss of h with respect to the function, the target function f, and the distribution d to just be the average loss over the example. So this is fairly standard. We have a distribution over example. We have a target function, which is our assumption on how the world is labeled, and the hypothesis is suffering a loss that is just the average over random examples. Okay, so this is just definition. So what is learning? I'll give a somewhat more general definition of a learning model. So I'd like to think of learning as simply as a game, which has a couple of interesting players. So first, we have the target class, which is basically functions from input to labels. And this captures our assumption about the world. So we have examples, I don't know, images of dogs and images of cats, and the label dog and cat. And then there's a set of functions that captures, well, how is the example mapped to the label? So this is primarily our assumption on the behavior of the world. The second class is the hypothesis class, which is functions from the examples to some number in R. Which is the choice of the learner. So here I'm separating between the target class, which is the functions that label the world, and the hypothesis class, which is the functions that the learner can output. Okay, so this is our choice as learners to choose a hypothesis from the class H, and the target class, which labels the world, is the class F. We also have the distribution space, which is just a set of distributions that captures, again, our assumption about how the distribution of examples behave in the world. And we have an oracle, which is kind of like a mysterious being. I will not explicitly define it, but we can think of it as an all-knowing entity that is the guy that we're competing with. And finally, we have the learner, which is the learning algorithm. This is us in a sense that we want to learn the problem. So what is the game of learning? The oracle picks a function from the function class, a distribution from the distribution class, and he will do so in order to fail us, let's assume. And the learner, which wants to get a good loss on the choice of the oracle, can query the oracle about its choice. You can ask him predefined questions about what the oracle chose. So the oracle chooses F and D, and we can ask him, well, how does this F behave in this scenario, or whatever. And in the end of the game, the learner suffers the loss, which is the loss that we defined previously. So this is just the loss with respect to the choice of the oracle on the hypothesis that the learner outputs. Is this clear so far? So this is quite a general scheme. Okay, so what is learnability in this game? So assume we fixed all the players of the game. We say that the target class F is learnable efficiently if there's a Turing machine that runs in polynomial time, polynomial in the problem parameters, the dimension, and these epsilon and delta, such that with high probability, with probability over greater than 1 minus delta, this algorithm returns a hypothesis with small loss, with a polynomial number of queries to the oracle, right? So we can ask a polynomial number of questions, run in polynomial time, and then return a hypothesis that has a good loss with respect to this learning. So if we manage to do so, then we would say that the target class is learnable. So maybe the most famous form of this learning and learnability is the pack learning setting, where the oracle is simply the examples oracle. So all the query to the oracle is just give me an example, sample an example from the distribution D, and give me the label with the function that you chose. And usually we take the set of the set of distribution to be all the distributions. So the oracle can choose whatever distribution over examples that he would like. And there's two variants of this model. One is proper learning, and the other is improper, which depends on whether we allow the learner to output a hypothesis from the class of the target function, right? So H would be equal to F if we're doing proper learning. And if we're doing improper learning, then the learner could choose whatever function he would like. Okay, so this I guess anyone who took introduction to machine learning should be familiar with this. But there are other models of learning besides pack learning, and they're also interesting to study. One sort of model, this is not very formally model, is what we in the community call deep learning. And the way that I want to define deep learning is a learning model where the hypothesis class is some parameterized function, and the oracle is the gradient oracle, where we can ask for a gradient in one specific point of the loss. And the learning algorithm would be simply gradient descent. We're just doing gradient updates with respect to the answers of the oracle, with respect to the gradients that the oracle returns. Okay, so we have some learning rate eta and regularization thing turn lambda. But this would basically, when I say deep learning, this is what I mean for now. So this is another model that I'll focus on. You can define other models. Distribution-specific learning would be the case where the set of distributions is just some fixed distribution, say the uniform or Gaussian distribution. We also have statistical query learning or correlation query learning, which would also play an important part here. Here, the oracle is the correlation query oracle, where the oracle gets some function, and it will return the correlation of this function with the choice of the oracle, with the choice of F. And this will be accurate up to some time. So this is another learning model, and there are other you can define. It's a very rich family of models. And all of these models, this is like a very beautiful, beautiful game to play, because whenever you change something in the model, you can give more power to the learner. You can assume less or more about the world, and this opens a very rich structure of problems where different classes would be learnable or not learnable efficiently under different model assumptions. So maybe the harder one is the proper pack learning in this case. So there are some functions that are not properly learnable, but are improperly learnable. There are some functions that are not improperly learnable, but you can learn it if you assume that the underlying distribution is uniform, et cetera, et cetera. So different definitions of these models give you different learnability results. So some classes would be learnable under some models and others under other. And maybe the most interesting thing about this whole game is focusing on neural networks. So I'm just assuming that everyone knows what neural networks are, because I guess you do. So and my focus here would be primarily on neural networks. So what's interesting about this learning, this general form of learning, is that neural networks, which is, I guess, the most used target or hypothesis class today, are unlearnable under every plausible learning model that you can consider. So we can play with these definitions a lot. Some of these models would make sense. Other would be very trivial. But under any model that would make sense, that would capture something about learning in practice, neural networks are unlearnable. So this is kind of like the main point that I want to convey.
When you say neural networks, do you necessarily mean feed-forward neural networks, or is it like every fancy architecture you can think of, also like convolutional and recurrent?
Pretty much everything, pretty much the simplest network that you can think of, one hidden layer with a few neurons, so if the number of neurons is not very small, if the norm is not very small, if some constraints are, if you don't have very hard constraints on what you call neural networks, then this becomes unlearnable probably in any model that you can consider. So I'm not giving. I'll give a formal definition of neural networks when we get to like the positive result. But for now, it works for pretty much any architecture, any activation function you can, and any learning model that you can think. Right.
And is it also like every learning algorithm, or is it just gradient descent like? Or
so yeah, it's a good question. There's open questions in what you can say on general learning algorithms. As different learning models require different hardness assumptions. So in some cases, you assume P is not equal to NP. Other cases, you need cryptographical hardness assumptions. So it depends on the model, but pretty much every model that we consider, we have negative results. So I don't want to go into the specifics of every model because it will take a very long time. I will focus on deep learning. So, but you can kind of believe me. At least as far as I know, there's no positive learnability of interesting neural networks. So one specific result that I want to focus on, and this I will sort of prove, is that neural networks are not deep learnable. And by deep learnable, I mean that they're not efficiently learnable using deep learning. And this, I guess, should sound very weird to anyone who's focused on practice of neural networks. If neural networks are not deep learnable, then what is deep learning? Right? It doesn't make sense. But this is the theorem, and it's valid and it's true. So let me prove this. So I'll prove it in a very specific case, but it kind of holds a lot generally. So I'll assume that the initialization of the neural network, again, it doesn't really matter what the architecture is such that the output of the network is bounded between -1 and 1. The oracle is not an exact gradient oracle. This is something that we can very rarely get. The gradient is an approximate and clipped gradient oracle. And you can think of it, well, if you're calculating gradients on a finite precision machine, right? So you can't expect to have it like up to infinite precision. You always have it up to some fixed precision, and the gradients are always clipped because you can fit the infinity in the finite precision machine. So this is a fairly practical assumption, and I'll prove it for the uniform distribution, which is an easier case supposedly than learning under any distribution. So to show this negative result, I need the concept of what I call the variance of the target function. So some technical definition. So for two functions f and g, we define an inner product with respect to d to be just the correlation or the average of the product between these two functions, and this defines a valid inner product. And the norm of this, and the norm of the function would be just the norm that is induced from this inner product definition. So fix sum distribution. So I always have in mind this this target class f, and in our case we think of f as neural networks for now. And for some distribution over the target class f, so some distribution over neural networks, and some function phi, we define the variance of f with respect to mu, this distribution, and phi, the function, to be just the average correlation or the average variance of the inner product between f and phi, right? So this is a technical definition, and the variance of f, the variance of the target class, would be just the worst case distribution. So this would be the worst distribution that you can choose that gives us the smallest variance for the best choice of phi. So just to give an intuition into these definitions, so we can think of mu as the distribution of functions that from which the oracle would choose. So the oracle wants to fail us, and phi would be the query to the oracle. So we want large correlation with the target function. So we want a query that will give us large correlation. And if the variance is very small, it means that the oracle can choose f from a distribution such that we will not be able to get good correlation with the choice of the oracle. So we won't be able to learn something about the choice of the oracle. Is this clear, or do you want me to clarify anything? Are there questions? Okay. So this was just a formal definition, and I'll give sort of a hand-waving argument for why function classes with low variance are hard to learn, and this is true specifically for correlation statistical queries. So again, if the oracle is a correlation query oracle, meaning that it accepts queries phi and returns the inner product or the correlation up to some tolerance tau, then any algorithm will need a number of queries that depends on 1 over the variance of f, right? So this means that if the variance of f, the variance of the target class is very small, it's exponentially small, then we'll need an exponential number of queries to the correlation oracle to be able to learn. Okay, so this is the theorem, and the proof is kind of the intuition that I wanted to give. Say we have some worst case distribution that makes this variance very, very small. So the oracle can simply sample a function randomly from this distribution, and by our definition, no matter what query that we would ask, the variance of the correlation with this query, or the magnitude, the average magnitude of the response to our query, would be very, very small. So on average, over the choices of the oracle, we will not have any signal in the response of the oracle. And since we assume that the oracle is approximate, so it gives a response that is accurate up to some tolerance tau, if the correlation on average is very, very small, then there's only a very small number of functions that have high correlation with any query that we will choose. So in order to gain some signal about the choice of the oracle, we would need to make a number of queries that grows It grows with yeah, it should be the opposite. Tau squared over variance of f, right? So it's kind of hand waving, but you can formalize it fairly easily. So if the variance of f is very small, then the correlation query oracle would need a lot of queries, and therefore it will be hard to learn. And I'll show in a bit that gradient descent is sort of, you can think of it as accesses to a correlation query oracle. Is this clear so far? Okay. So we said low variance is hard to learn. And now to show you that neural networks are not learnable, let's compute the variance of neural networks. So we have a very interesting set of functions, which is the parity functions over x. So this would be just the product of some subset of indices from some subset of bits from the input. And this is just a set of functions, and you can think of it as monomials of varying degrees. So one fact about this set of functions is that it is an orthonormal basis with respect to the inner product we just defined. And another fact that you can prove to yourself is that you can compute parities with neural networks. Okay, so and this holds for probably any interesting architecture neural network. And what this helps us to show is that the variance of some set of parities is 1 over the size of the set. So the proof is just an implication of Parseval's inequality or Parseval's equality. If you're familiar with this, fine. If not, then you can just believe me. But what the reason that this holds is because we can always look at some function on our query as a sum of parity functions, and we can show that it is not possible that it has high correlation with more than a small fraction of the parity functions. And the result from this is that the variance of neural networks is exponentially small, and this is because they contain all the parities, and the number of parities is 2 to the n, right? So there's an exponential number of parities, and therefore the variance of neural networks is exponentially small. So if you followed so far, it should be you should already be convinced that neural networks are hard to learn. And this is, again, we're just using here some assumptions and a reduction to the correlation query oracle. So what this basically means that if you initialize your network in a small enough regime, then your first iterations of gradient descent will be just queries to a correlation oracle, and then you cannot learn if you make less than a number of steps that depends inversely on the variance of the function class. So since the variance, if the variance would be exponentially small, then this function class would not be learnable, and this is the case for neural networks, and then therefore neural networks are not learnable. Any questions so far? Okay, so this. I just want to say that it follows fairly simply from the definitions. Okay, so this is the conclusion, and it's I guess surprising, but also true. So again, neural networks, as we said, are not efficiently learnable under any plausible learning model, and this is true specifically for deep learning, but also for other models. However, in practice, as I guess most of you are aware of, neural networks are performing quite well. They solve a multitude of tasks, and they perform much better than any learnable class, right? So I don't know, half spaces are learnable in some or most of these settings, half spaces over embeddings of the input. But neural networks perform much better than, say, kernel SVM, which is used to learn these learnable classes. So it seems that there's something missing, right? So we defined all this very interesting model of learnability, and what we got in the end is that neural networks are not learnable. There are some classes that are learnable, but neural networks really beat all these classes in practice, right? We often observe that neural networks perform much better than learnable classes. So what's missing here in this type of field? So one answer, I'd like to call the skeptic's answer, is that nothing is missing, right? Neural networks are unlearnable, but in fact, when we're training neural networks in practice, we're not learning neural networks, we're just doing a glorified mode of kernel learning or random features or stuff that is already learned. So somehow in practice, we're not really learning neural networks, we're learning learnable classes that are that we already have had in the past, but maybe we just found a better kernel. So we're in fact just doing kernel SVM, but with a better kernel. And there's some supporting evidence to this kind of claim, because there's a large number of papers that already show that when we train very large neural networks, or when we take the size of the network to infinite, then in fact we're doing something like random features or kernel methods. So in some settings of neural networks, this is actually what happens. Actually, when we're training neural networks, we're just doing kernel methods or random features with the more fancy mechanism, more fancy and much more expensive mechanism, right? Yeah, again, I'm just assuming that everyone knows what the kernels are. Kernel SVM, random features would be just faster implementation for kernels. Okay, so I'll just guess that if you have questions, then you'll feel comfortable to stop me midway. So I'll just go on. Okay, so this leads us to maybe the main question here is, are deep networks just glorified kernel methods, right? So neural networks are not learnable in any model that we can think of. And in practice, in some settings, neural networks behave very similar to kernel methods with some sophisticated kernels. So maybe we're just missing everything. Maybe neural networks are just kernel methods and we're wasting so much GPU power and money and whatever on training these huge models when we could just use the same techniques for learning kernel methods that we had in the 90s. Right, so this seems like an important question. Right? So I'll try to answer it. I'll try to give a negative answer to this question. But before this, I'll try to convey the second point of this lecture, of this talk. So in order to answer this question, I want to make a shift in our view of learning models and all the things that I discussed previously. And this shift would be based on moving from understanding function classes to understanding distribution classes or distribution families. So what is a distribution family? Distribution family is just a set of pairs of function from the target class and distribution over the input, or distribution from the input space. So we have just a set of pairs. I will denote it by A. It's just a set of pairs of function and distribution. Right? So this would be our distribution family. And we're mainly focusing on asking whether some function classes, say neural networks, are learnable or not learnable. So this would be the learnability question of neural networks. And in some way we failed in this process because we found out that the very practical function class is basically unlearnable. So instead of focusing on learnability of function classes, I suggest that we we move to focusing on learnability of distribution families. Again, this is not so new. I mean, there's some of these definitions are already go back to the 90s, I guess. But I feel like most of our focus is usually on learnability of function classes. And what I'll suggest here is to move to study learnability of distribution families. And to do so, we'll just redefine the learning game as follows. So we had an oracle previously that chose a function and distribution, and now we're just forcing this oracle to choose a pair of function distribution from our distribution family. And in this case, we will say that our distribution family is efficiently learnable if it's learnable with respect to this new game. So everything that we change here is, instead of giving the oracle the freedom to choose a function and then to choose a distribution however it likes, we force him to choose some function distribution pair. So in a sense, this distribution family really captures our assumption about the world in a more strict way that we allowed previously. Right, so you can't just arbitrarily choose the distribution of examples and arbitrarily choose the function. You need to choose them in some way that that really satisfies assumptions about the world. Okay, so this is kind of like the shift that I want to do, and I will use this new mode of learning to answer the previous questions of neural networks versus kernel methods. Okay, so I'll focus on comparing two hypothesis classes. One is the class of linear models, which is basically just linear classifiers over some fixed embedding of the input. So we have some embedding of the input psi to a higher dimension space of dimension n, and a linear classifier over this embedding of the input. And the second model would be ReLU networks. We're focusing on ReLU 6 from not so interesting reasons, but this is the network architecture that we will analyze. And this is just a standard ReLU network with one hidden layer over the first. Okay, so these are the two models, and the question is that we ask is, are there in some way the same thing when we're training them in practice? And the result that I want to show, again, so this is from a NeurIPS paper, a paper with Amit Danieli that will be published in NeurIPS. So this is our main result there. What we show is that there exists a distribution family A such that first, this distribution family is deep learnable with ReLU networks. And second, this distribution family is not learnable, doesn't matter about what learning model you choose, with linear models over any choice of such size. So it doesn't matter what the embedding is, it doesn't matter what the learning model is. So this same distribution family would not be learnable using linear models, right? So the corollary here, the result, what you should maybe expected is that ReLU networks are not just glorified linear models in this sense, right? That there exists some distribution families or problems or assumptions about the world where we can deeply learn neural networks to solve this problem, but we cannot learn any linear model to solve the same problem. Okay, so this is our result. So let me define this distribution family. It will appear somewhat synthetic, but it's good enough to prove the result. So we define it as follows. It's just a uniform distribution over the input with probability 1/2. So with probability 1/2, we just choose a uniform set of bits. The input is a set of n bits normalized to the unit sphere. And this with probability 1/2. Probability 1/4, we for every subset I, we pick, we choose all the xi's that are in the subset to be all plus 1, and then the rest of the bits we select uniformly, and then with probability 4 we fix all these indices to be -1, and then pick the rest uniformly at random. So for every subset I, we can define such a distribution where with probability 1/2 we're just choosing uniformly, and then the rest of the time we make sure that the bits of the this subset agree with each other always. Yeah, and again here we would use the parity functions, and we take the distribution family to be just these pairs of parities and the distribution that we just defined for some fixed subset of fixed sides. Okay, so this is the definition of this distribution family. So there are two parts of this this result. The first part is the positive part, where we show that for certain values of k, this family is deep learnable using ReLU networks with polynomial width and polynomial runtime. This means that gradient descent will be able to find a solution to this problem defined by distribution family. We have some. I wouldn't get too much into the details. So we have some assumptions on the initialization and the choice of the learning rate and the regularization. And what we basically show is that the first step of gradient descent would learn to ignore all the irrelevant bits and focus only on the relevant bits. So we'll have some neurons that really zero out all the irrelevant bits of the parity and really focus on the relevant part of the parity. And then we can show that this is a good enough representation, so we can learn to separate this parity problem by only updating the second layer. And we show that indeed this is what happens when we run gradient descent, right? So for this distribution family, what we show is that ReLU networks actually succeed. So this was the positive part. And the negative part would be to say that for any linear model that you choose, you cannot approximate the loss of you cannot approximate the loss of this distribution family unless the number of features or the norm of the classifier is exponentially large, right? So we'll lower bound the loss of any linear classifier over a fixed embedding unless the number of features or the norm is very large. And here again, we'll go back to the definition of variance that we had in the beginning, and amazingly, it plays a role in this theorem as well. And we will use this technical lemma that says that if the variance is very small, then we can lower bound the norm to be very, very close to a trivial classifier, a trivial loss of one. So that we can lower bound the loss of the classifier and show that you cannot do better than a trivial approximation of the set of functions. And to show the negative result, we just plug in the results on parities that we had in the previous part of the talk. So we know that the variance of parities is very small. Therefore, you cannot approximate parities with linear methods in this form. And by the definition of the distribution family, this shows us that linear methods are not very good at, cannot approximate this parity problem beyond a fixed. When do we finish? It's like.
You have 20 more minutes.
I have 20 more minutes?
Yeah, 1 hour in total.
Okay. Yes, so any questions about this? So I guess maybe the surprising thing here is that the variance that we use to bound the learnability of neural networks in the previous part plays a role here in showing that the same parities are not cannot be approximated well by linear classifiers. But then again, it should be kind of, yes.
Sorry, can I ask a question?
Of course.
So I don't have intuition about this proof because if you think of the two-layer network that you used in the constructive proof, mm-hmm. I can take the representation in the first layer, define that to be psi, yeah. And then I have a linear classifier in that space. So why is that not a counterexample? Okay,
so this is a good question. So what's the difference? Okay, this is really the core of the difference between neural networks and kernels. right? So in neural networks, in kernels, I first have to fix this psi. Before I asked the oracle anything, I come with my psi, which is the kernel that I chose, and then the oracle can answer whatever, and I need to learn this. And what this shows that if you fix your psi, and you need to be good on all the parities of size k, then you cannot do this. Of course, you could be good on some parities, but you need to be good on all the parities of size k. And since you're fixing your representation, you won't be able to do it. So this is, you start, before you even ask anything, you decide what your representation is. So this is kind of like the major problem. In neural networks, on the other hand, I can change the representation after I ask the oracle, will give me some information about the function. So this is in a very high level the difference between the two. So
okay, thanks.
Yeah, okay. So yeah, but it's important. It's really the core of what's happening. So in neural networks, I'm changing the representation. Even at the first step, I moved from some random representation that I chose to the relevant representation of the bits of the input. So this is what happens here, and this is kind of the gap between.
And if you have a kernel that tries a lot of random representations, I guess that's the negative result. You'll need an exponentially large number.
Yes. So the problem is that you have an exponential number of parities. So if you try to choose even half of that, then you pay a price that they expect, right? So you need to really try a lot of this. Of course, if you allow an exponential number of features, then you'll beat this method. But yeah, we don't allow this. Okay. Yeah. Good. Okay. So before I show the proof for this lemma, I just want, maybe it's important to understand why it works and why it's so related to the learnability result. Right, so if you recall, we showed that if the variance is very small, then it's hard to learn. And now that we show that if the variance is small, then it's hard to approximate using linear methods. But then all you need to connect here is that, well, linear methods, you can learn efficiently, right? And fairly easily with, say, gradient descent. So if it's hard to learn parities and you can efficiently learn linear separators, then this means that linear separators cannot approximate parities, because otherwise you'd be able to learn parities, which contradicts the previous result. But I'll just maybe I won't go into all the details here, but kind of the outline of the proof says that, well, we can, using some convexity problem, we can lower bound the loss of linear classifiers by the loss at zero and some term that depends on the loss of the gradient at the point of zero. Right, so it's the loss in zero, which is just 1 for the hinge loss, minus something that depends on the norm of the classifier and something that depends on the norm of the gradient at initialization. And then we do sort of the same tricks that we need for hardness of learnability to show that the norm of the gradient at the point of zero is going to be very, very small in this case. So we'll need either a very large number of features or a very large norm for the classifier to get something that is beyond trivial. So this is kind of like the end weight version. Okay, so more details on this is actually also in the other paper with the HUJI. I'll give all the references. Okay, so in the time I have left, I just want to discuss what we have so far and what can we say about learnability and deep learnability, specifically of distribution family. So far, what I showed is that neural networks are not learnable and they're not deep learnable. And we asked, well, does deep learning go beyond traditional learning? Can deep learning learn the unlearnable, quote unquote? Can it do better than kernel methods? So the answer is yes, but it's yes only if we focus on distribution family. If we redefine learnability using distribution families and not function classes, then this new perspective of learning really captures something on deep networks or deep learning that goes beyond traditional problems that we can learn. And then, of course, the very interesting open question is, well, which distribution families are deep learnable, right? Maybe this is kind of like the holy grail of all this exploration. We have this magnificent mechanism that's called deep learning, and sometimes it fails. We know this theoretically and practically. And we really want to characterize deep learnability, right? Which distribution families are deep learnable? So if we focus on function classes, then nothing interesting is deep learnable, and we're deep. But if we're focusing on distribution families, then things become more interesting, and now we can ask ourselves, well, which distribution families are or are not deep learnable? So I don't have an answer to this question. It's, I think, a fairly big question, but I'll answer a somewhat simpler question, that is, which distribution families are not deep learnable? All right, so this
Can I ask a quick question?
Yes.
So since you're mostly focusing on feed-forward neural networks, right? So you're mostly asking the question like what kind of things you can learn with deep neural networks that you cannot learn with linear embedding and other learning classes. But we know from empirical evidence that like the main kicker of neural networks is when you try to use non-standard architectures, like when you have some weight sharing that is appropriate for a certain domain. So that's where you get most of the benefit from using neural networks. I don't know many people that actually use just feed-forward networks in real life. I think it's not considered that a good algorithm compared to classical machine learning algorithms. So is it something you tried to analyze and to see like where the advantage comes from in those cases?
Yeah, it's a great question. I actually have also works in this direction, but not for this talk, of course. It's a great question. I just want to mention that all the hardness results, all the negative results, pretty much hold for any architecture of network that you can try. So what we show for hardness is pretty much works for every architecture. For positive results, there are cases, and again, I have a very, very recent work on comparing convolutional networks to fully connected networks, and indeed we can show that that in some cases there are problems that are not deep learnable using fully connected, but are deep learnable using convolutions. I will not talk about this in the last 10 minutes of my talk, but yes, it's a very interesting direction, and of course, yes, deep learnability in the way I defined it doesn't assume anything about the architecture, but of course, if you take some architectures, convolutions or LSTM or feed forward and start comparing them, then you can understand a lot. But here I'm more on the basic level, like even this fully connected, like the very, very simplest network that you're concerned with, even there we're not really understanding things. So again, negative results hold for everything. When you start going deeper into the architectures, then yes, you can see computational gaps between fully connected and convolutions. You can see the effect of weight sharing, of local connections, etc. So yes, it's a great question, but I'm more on the basic level in this sense. Okay. Okay. So yeah, I'll finish with the negative result, which states which distribution families are not deep learnable, and again, this is fairly for any architecture that you would choose. So it's not capturing the whole image, it's just kind of the lower bound part of characterization of deep learnability. So again, I go back to the definition of variance that I had in the beginning. So this was for some choice of distribution, some choice of query, the worst case variance that we would get. And notice that I can really define exactly in the same fashion the variance of a distribution family. So we had the variance of a function class, but really just plugging in the definition of the distribution family, we will get the variance of the distribution family. It would be instead of choosing randomly a function, we choose randomly a function distribution pair, right? So this this is the variance of the distribution family, really just very similar to what we showed. And again, recall the result that we have, that if we have a clipped approximate gradient oracle, then we need to make a number of steps that depends inversely on the variance of the function class. And actually, I will not show this, but if you take really exactly the same proof and replace A with F and variance of F with variance of A, you can show exactly the same result for the deep learnability of A, right? So we had that the variance of F makes F hard to learn. And here, if the variance of A is very, very small, then the distribution family A is not deep learnable, right? So we have exactly the same dependencies as before. Distribution families with low variance are hard to learn with deep learning. But this is not really enough because we want to say something. We want to bound this variance term in a way that will allow us to give concrete bounds for distribution families. So we really want to bound it in terms of something that we can actually work with, not these abstract definitions. So to do so, I'm just identifying a distribution family with a matrix, which has the rows of the examples, and the columns are just the elements of the distribution family. And in each entry of the matrix, I just write the value of the function times the value of the distribution in this entry. And it turns out, really, again, it's a two-line proof that the variance of this distribution family really depends mainly on the L2 norm of this linear operator, on the operator norm of this matrix that we just defined. So we can identify distribution family with matrices, and if these matrices have a low operator norm, then the variance is small, and so we cannot learn. Right, so this is basically the bound we can. And again, I won't give here all the details, but using this type of bound, we can show very interesting results. We can show that DNFs are hard to learn with deep learning or with correlation queries, with the bound, with an exponential lower bound that really matches our upper bound. We can show that they are hard to approximate using linear models. We can show hardness of learning of Boolean circuits, and we can show again hardness of learning with correlation queries. And these lower bounds really match the upper bounds, the known upper bounds for learning DNF. And notice here that although we're talking on sort of this new perspective of learning, if we achieve a lower bound in this distribution family setting, it directly implies lower bounds in the distribution-free setting that we usually have, right? So we're only limiting the oracle in a sense, right? So if we're forcing the oracle to choose the function distribution pairs, and again, and even in this case, it's hard to learn that. Of course, it's hard to learn in the standard case of learning. So if we get lower bounds here, interestingly, this also implies lower bounds in the classical model of learning. So we gained something, even if you don't believe in this new perspective of learning and learnability. And in fact, using very similar techniques, very, very, very recent result from like last week, was able to show hardness of learning of function classes that cannot be approximated using low-degree polynomials. So any function class that is not essentially low-degree polynomial cannot be learned in the distribution-free setting. In this case, using very, very similar techniques to what we are using and what we show. So this is all the details of our work is it's a paper on archive for now with the HUJI. And there's a follow-up work, a very nice extension of these results that really give a very fundamental characterization of learnability with the correlation curves. Again, in the standard classical. Okay, so I'll just summarize, and if you have questions, then feel free. So again, traditional learning theory, as we defined in the beginning of this talk, cannot really capture what's so good about neural networks. Like classical learning theory doesn't see neural networks as especially good, even worse. It sees it as an unlearnable creature and just don't use it. So if you want to see the difference between neural networks and classical methods of learning, classical models of learning, we really need to focus on learnability of distribution families, because if we're only concerned on learnability of function classes or learnability of neural networks, then everything is unlearnable. And so our main goal, which is for now remains open, is to understand which distribution families are deep learnable. And ideally, what would be great to achieve is to say, well, I have an exact characterization of deep learnability. A distribution family is deep learnable if and only if it satisfies something. So this is an open and a very interesting question. For now, we have only one direction where we show that if the distribution family or some representation of this distribution family has a low norm, then it has a low variance, and then it's hard to deep learn, right? So we have maybe one direction in this, and this characterization, not yet the characterization, but really, I think this is kind of like the ultimate goal that would be very interesting. Yeah, so I guess that's it. Yeah, the two references are the paper with Amit and the paper with HUJI. And if you'd like to learn more about this, then feel free to read on your own. Yeah, I mean, if you have questions, then ask them.
Can I ask a question? What was the motivating? I mean, what drove you to choose the definition of distribution family? I mean, how did you get there? I mean, I see the value, but
so again, it's not my definition. I mean, it goes back to like a paper from '94, like the agnostic learning and these type of works. So it's in the literature if you look into it, and really the motivation here is that if you stick with learnability of function classes, that you simply fail to say anything interesting about learnability. So and we've done it for a long time. It's still very interesting, right? It's still very interesting to understand which function classes under which models are learnable or not. They're very interesting, very rich literature and very interesting open questions. But it seems that however we look at this problem, it doesn't tell us anything interesting about neural networks. So this is kind of the motivation.
All right, thank you.
Anything else?
Any other question? Okay, so I want to thank again to Eran Malach for this really amazing talk. And see you all next week. Same time, same link. Okay, thank you, Eran.
Thank you.